Okay, welcome to chapter 25. It's the last chapter in unit 6. And today we're talking about paired samples and blocks. So what you're going to notice is that this is very similar to what we've been doing for the last chapter, which is with the T samples. Okay. And the only difference is right now we have paired, or with this chapter, we have paired data. So data are paired when the observations are collected in pairs, or the observations in one group are naturally related to observations in the other group. Okay, so and paired data arise in a number of ways. Perhaps the most common is to compare subjects with themselves before and after a treatment. So if you timed how fast somebody did something without, I don't know, some sort of memory game or something like that, how quickly they were allowed to memorize something, and then you gave them some sort of treatment, and then you timed each person again as to how quickly they could remember something, you would compare each person to themselves. So you have subject 1, and then after the test, you measure subject 1 again, and you're comparing the difference between those two. That's an example of paired data. So you're not looking at one whole group versus the other whole group. You're looking at people who are matched with somebody else, or people who are matched by themselves with a before and an after. So when pairs arise from experiment, it's called blocking. So blocking should be a word that you have in your vocabulary list. And when they arise for observational, it's called matching. Okay, it's called matching. All right, so an experiment would be the timed test where you're giving them some sort of treatment and then you're timing them before and after. And an observational study, you're watching and comparing a person, how they behave, and then after a treatment, comparing how they behave. Okay. All right, so if you know the data are paired, you have to take advantage of it. There's not a test to decide if there is matching involved. You have to look at how they were collected and what it actually means. Okay, so when you read the scenario in a given problem, you're going to determine if the data are matched or if it's a two-sample t-test like we've done before. So on the quiz, where the example was about beats of music in dance music versus beats in the top 200, those would not be paired because they really have nothing to do with each other. Okay, you have the beats in the dance music and the beats in the top 200, but they have no relationship to each other. So that's one of the things that you're looking for. Okay. So once we know if the data are paired, we examine the pairwise differences. Okay, it becomes a one-sample t-test because all we're looking at is the differences. So my example of you're timing them, you give them a treatment, then you time them again, all we care about are the differences between the timing. We don't care about the timing with each one of them. Okay, it's the differences that we care about. Okay, so now that we have only one set of data, we use our one-sample t-test. So mechanically, a paired t-test is identical to the t-test with a one-sample. Oops, I forgot to underline that. So the one-sample t-test. And the sample size is the number of pairs, not the number of times they were tested or something like that, but it's the number of pairs is what n is. Some people are still having trouble figuring out what n is, so make sure that you note that. Okay, and there's some examples coming up later. So as far as the conditions, mostly the same as what we've talked about. There's a paired data assumption. So you're going to list that the data are paired. Okay. Independence, you're going to show that the differences are independent of each other. I have more and more people who are making a list of these, so we're moving in the right direction. Now what we need to do is start explaining these in the context of the problem. So you would explain that the differences between this and this, that they are independent of each other. Okay, and there again, there's an example coming later. So randomness, we still have to look at randomness. We want what we want to know focuses on where the randomness should be. And the 10% condition, it depends. If the sample is really small, then we're not necessarily going to worry about that. So with the normal population assumption, we're looking at the nearly normal, but we're going to look at the nearly normal with the differences. So we're going to be paying attention to the histogram, but only with the differences. So when you get your calculator out and you input all of the data, you're going to be making the histogram just from the differences. Okay, so the paired t-test, conditions are met, we can go ahead and start, okay? What we're looking at is whether the paired differences are different than 0. Okay, so mu sub d is the mean of the differences. I'm writing DIFF, okay? And delta 0 is that is going to be equal to 0, that the difference between those is going to be equal to 0, and that's what the null hypothesis is. So when you see a paired test, you know that the mean is going to be equal to probably 0, because we want to see that there is no difference. That's what our null hypothesis is going to be, that there is no difference. So here's our statistics. So T sub n sub 1, remember n, or not n sub 1, n minus 1 are the degrees of freedom. So however many paired groups there are, or how many differences there are, n minus 1 is the degree of freedom. The d bar is the differences. Okay, so this is the mean of the differences. Okay, and so minus the delta 0. Okay, so it's probably going to be 0. It depends on what it is in your null hypothesis, and we're going to divide it by the standard error. Notice these are looking exactly the same as we've done with the z-score and the t. You just have to make sure that you are choosing wisely with what test you're going to use. Okay, and remember, n is the number of pairs. So the standard error, again, is going to be the standard deviation we find with the sample, and you'll find that on your calculator. And again, I have some screenshots later that will go through this with you. And the square root of n, where n is the number of pairs. Okay, so that's the same standard error that we've been using. When the conditions are met and the null hypothesis is true, we use the student's t-model, n minus 1 degrees of freedom, and we find what the p-value is. So we use the t-CDF to determine what the p-value is. Okay, confidence intervals. Okay, so when the conditions are met, we're ready to define the confidence interval. Okay, so d bar, the mean of the differences. Right here, the t asterisk n minus 1, remember that depends on the confidence level that you choose. And again, later in this video, I have some examples of what the screenshots should look like. So this you're either going to find from the chart or off of your calculator. It's not something that we calculate. Okay, and then the standard error of the mean of the differences we've already calculated. It's right here. Okay, all these formulas should be written down in your notes. Okay, and I just explained this. Okay, so blocking. If we were comparing the differences or the wife's age to the husband's age, this box plot really doesn't tell us anything at all. It just tells us what the ages of the wife is and the ages of the husbands are, but it doesn't allow us to compare anything together. So really this is, you won't use box plots in this because it doesn't show us anything at all. So in this case, we have paired data. Each husband is paired with his respective wife, and the display we're interested in is the differences in the ages. So all of these values here are how many couples have that as the difference in their age. Okay, my husband is almost 4 years older than me, so we would be right in this category, up in the tall part of this. Just FYI. Okay, so pairing removes the extra variation that we saw in the side-by-side box plots and allows us to concentrate on the variation associated with the difference in age for each pair. Okay, so that's why we do it this way. So what can go wrong? Don't use a two-sample t-test. Don't use a two-sample t-test for paired data, and don't use a paired t method when the samples aren't paired. Don't forget outliers, and don't look for difference between the means of the paired groups with side-by-side box plots. We need to compare them each 1 to 1. Okay, so pairing is a very effective strategy. It's used very often especially if a pre-post test model is used. It helps control the variability between individual subjects. Analyzing data from matched pairs requires different inference procedures. Paired t methods look at pairwise differences, and we test the hypothesis based on the differences. we think about the design of the study before we proceed with inference. Okay, so here's an example that I have for you. Make this a little bit bigger. Okay, so field workers for a health department compare driving mileage on a 5-day work schedule with mileage on a new 4-day schedule. So field workers mean that they're out driving around a lot for some health department. So whether they're going to people's homes or they're going to different hospitals, but they're driving a lot. So they want to know, are they going to be driving less and possibly saving money? Or are they going to be driving more if they change to a 4-day schedule? Okay, so they want to know. We're going to look at the pairs. So this is paired because, for example, we have Jeff. This is how many miles Jeff went in one 5-day, in his 5-day mileage. And here's how many miles he went in 4 days. And so here is the difference between those. This column is what we care about, and that's why it's a paired test. We don't care about how much they drove each time. We care about over the week. Is there any significance in the difference? Okay, so first let's look at the conditions. So we have the paired data assumption. Okay, the data are paired because each value is the mileage driven by the same person before and after a change in work schedule. The independence assumption, the driving behavior of one person doesn't affect the driving behavior of the other person. It's randomized this time around. If we did it another time, it'd probably be randomized again. They're not necessarily going the exact same places. And it is nearly normal. If we look at the histogram right here, we see that it is nearly normal. Okay, so the data that's on this slide, I put in my calculator to refresh your memory on how to do that, just in case you weren't sure. So if you want to pause the video and enter this data, just this difference column, then you can go sure and follow my slides and make sure that you know how to do that. Okay, that's on the next slide. Here, I'll show you what it looks like. So in the edit list, I put in all of these numbers, and then I went over to calculate, same stat menu, one var stats, and this is what I come up with. So here is the mean of the differences. This is the one you want to use. SX is the standard deviation for this sample. This is the standard deviation for the population, and we don't want to ever use that one. So you can just cross that one off. You want to use the S. Think S for sample, and that's the one we want, and it tells you how many pieces of data we have. Okay? All right, so I want you to notice what the alternative hypothesis and the null hypothesis are. The null hypothesis is that there is no difference in the mean. And the alternative hypothesis says that it's not 0. Okay, it didn't say it was greater than or less than, it just said is it different. So let's go back here. Is it okay to, we already answered that question. Where is the question here? Okay, is there evidence that a 4-day work week would change how many miles the drivers work? Or the workers drive. Okay, so we don't care which direction it goes. We just want to know, is it different? Okay. All right, so here's all our information. I would like you to get in the habit of writing this down so that when I grade your test, I know what information you used, and when the AP readers read your information, they'll give you partial credit for having this written down. Okay, so here's the standard error. So I use my standard deviation for this sample, the S right here, divided by the square root of how many pairs. Okay, and then here's my t-test, t sub 10, because that's how many degrees of freedom. And I just plop in all of these numbers, the mean, and then the standard error. And here is my t-value. Now, typically, that t-value is going to be greater than or equal to, or it's going to be in between -3 and 3. If you get like the number 100, you definitely did something wrong. So please pay attention to that, and that will help you figure out, okay, wait, maybe I made a mistake here somewhere. Okay. All right, it's a two-tailed test, so I have to multiply my p-value times 2. Here is what your screenshot should look like. We have t-PDF. Okay, and this is a mistake. It should be 2.86, and then my upper should be 99, my degrees of freedom. So this should be 2.86, and this should be 99 for my one tail, and then I multiply it by 2 to get 0.017. Okay. Another thing I want to point out is we're getting much better at writing here. The p-value is small, so I reject the null hypothesis. Small means that it's a very small percentage of time that it is going to be happening. Okay, so that's a good thing. All right, and then so you might want to pause the video here and write down what that the right here. It appears that changing the work schedule may reduce the mileage by workers. Okay, I'm going to pause the video here and then I will come back to this.